Thanks for joining this session. On this session, we are going to talk about our use of persistent memory at PayPal. And specifically, we want to talk about the advantage of that from a operational perspective. So my name is Vincent Chong, and I'm a senior MTS engineer at PayPal. I work in the group called Database Cloud Engineering. So today we have two speakers. My colleague will join me at the second half of the presentation, and her name is Deepti Sharma, and she is also a MTS engineer. So in this session, we are going to introduce a new NoSQL database called Aerospike that is in use at PayPal. And we want to use this platform to illustrate the advantage of using persistent memory. And obviously, the same advantage can be applied to different platforms. So first, we will introduce the footprint at PayPal of this platform. And we will talk about the architecture of this NoSQL database. And then we will talk about how persistent memory fit into the overall architecture. And then we will, as an example, illustrate the configuration that we have in this platform at PayPal. And then finally, Deepti will talk about the operational benefits of PMEM that is in this platform from OS patching perspective, which is following up from what Pramod just mentioned. We have a lot of OS patching and security patching activities. So this use of PMEM really comes into our advantage. So as a growing journey, we have been using Aerospike for 5 years now, starting from 2016, at which time we have actually 0 instance of Aerospike. As you can see, during the last 5 years, we have grown from a 0 footprint to a inventory of 2,000 hosts. And for these 2,000 hosts, we actually have about 150 clusters. And the reason why we have so many is because we form a cluster group of 3. So we actually have 50 cluster group. Each one of them has a primary serving live traffic and a local disaster recovery copy, which is a standby. And we also have a remote copy, which is in another data center, which is mainly for huge incidents such as, the entire data center went down, then we would fail over to the remote cluster. That's why we have 3 clusters per group. Now, and another reason why we have so many hosts is because at PayPal, since 2016, we have had very good success story, and a lot of teams within PayPal are requesting to use this platform. So today we are serving many different use cases. Just to name a few, the biggest use case we have is for fraud detections. As you know, our business is, big part is online shopping, right? So for each transaction, we have to determine in split second whether a transaction is legitimate or whether or not it is fraudulent. So that's why we require a very high performance platform and also which is high scalability also. Another use case which is important for us is for compliance check. Because we are a financial institute, we have to be compliant to a lot of regulations, and we constantly have to check different use cases and models and scenario whereby we have to be sure that we are compliant with the regulations. And then after a few years of use, we also use this platform to model graph relationships, which is simply another way of modeling our models in detecting frauds. And then as the mobile phone become very popular, we also have to capture the mobile device fingerprint, such as their MAC address, IP, the location where people are using the device, so as to detect frauds. And then also we would track a lot of different kind of events, like how many times a user log in, where they log in, and what kind of transaction they perform, something like that. So as you can imagine, this is a lot of data. So as an example of usage of this platform, let's talk about the diagram on the right-hand side. So we have a offline storage data, which is Hadoop, and we capture all this data from live transactions, and we stream all this data and we store them in Hadoop. And then we would have data scientists grab the data from Hadoop and perform different kind of analysis and form different kind of models and variables. And those will be loaded into our Aerospike NoSQL database in the red color. And then at the same time, we would have rules, which is encapsulated in our application layer. And then those application will fetch the model and variable and perform some kind of fraud detections. Now, all of these are happening in split seconds. So typically our timeout threshold for returning a data is about 100 to 150 milliseconds. And the Aerospike platform is serving more than 1 million transactions per second. So this platform has been able to allow us to handle 280 billion payments annually, approximately speaking. The numbers are changing. And we use this platform to replace a previous distributed cache layer called a terracotta server array. That particular platform only uses DRAM. And as you can imagine, DRAMs are very expensive, right? So by using this platform, we were able to reduce our footprint by almost 15 times. At the same time, we were able to improve our service level agreement with our clients. So because we can store a more accurate models and variable and have a faster work query time, we were able to reduce our false positive by almost 30 times over the years. And at the same time, enable a huge increase in revenue during all this year when we start using Aerospike. Not to mention the pandemic has somehow, increased our traffic substantially. So here we want to talk about the special architecture of Aerospike, and this is the reason why we can take advantage of the PMEM. This Aerospike platform has a unique architecture, which they call the hybrid memory architecture. And in this architecture, the data are stored in a fresh optimized storage layer, meaning the SSD, the NVMe type. And then the index to the record are stored in the DRAM. So this would allow us to get the benefit of the best of both worlds, because getting the index from DRAM is fast, and also storing the data in SSD is cheaper, right? So we get the best of both worlds. So now, because of our growing pain, so let me talk more about the economic of scale using the hybrid memory. As you can see from this pyramid, right? If we only use in-memory to store data, the amount of data you can store is only in the neighborhood of terabyte. But obviously, the advantage is that you have high speed and low latency. On the other extreme, if we only use SSD, obviously we would have a bigger storage for the same amount of money, simply because SSD is cheaper. But the drawback is that it is much slower, right? So it's about 25 times slower than in the memory. So this hybrid memory architecture would allow us to scale up to a bigger capacity without spending too much money. So for 5 times the cost, we can actually have 250 times of the storage of the DRAM. So at this juncture, as our footprint is already very big, we are faced with a lot of challenges. And the main one mainly is, we are faced with growing costs of supporting such a huge data volume growth. And then at the same time, maintain the same performance. Not to mention, with such a big footprint, we have a lot of operational challenge, such as the one that Pramod mentioned, right? We are constantly patching the OS, constantly patching the security loopholes, and also upgrading the software. And every time this happens, we have to do it to 2,000 hosts. So therefore, it is a very significant challenge from an operational perspective. So luckily, with the advent of persistent memory, now we have a new choice, because this persistent memory technology is a non-volatile media that fits in a standard DIMM memory slots. As you can see from the right-hand side, which is an example, The form factor is identical to a DRAM. So basically, we can swap out a DRAM and put in this persistent memory. And we're going to talk about what advantage the persistent memory offers. As I mentioned earlier, it is slower than DRAM, but it provides much higher throughput than the NVMe SSD. At the same time, it would provide much higher capacity than DRAM at a lower cost. And the persistent memory has two kinds of access methods. The first one is the block access, which operates like a storage, just like the SSD. In this configuration, the data flows through the file systems and storage stack as normal, just like SSD. The other one is the one that we use. It's called the direct access, which operates like a memory to get the lowest latency. And but then we have to use DAX in combination with the NTFS file system. Now, the reason why we can use this is because Aerospike has a tight collaboration with Intel, and they actually program their software to use this direct access method. Now, if you are like me, you'll be curious about how persistent memory can retain memory, even though if you power down the server, right? During OS, we have to bounce the server. So whatever was in the DRAM will be lost. As you recall, the index for our platform are stored in the DRAM. So when we power down the server or do the OS restart, we lost the memory. And then that means we lost the index. So however, Aerospike allows us to rebuild the index from the SSD, which is a persistent store. The duration to do that is more than 40 minutes. So every time we do that, it would take us 40 minutes per host. So so if you are like me, right, you're wondering how does persistent memory retain the data? The answer is that if you look at the diagram on the left-hand side, the yellow color and the green color is the cell, and it doesn't retain the state 0 or 1 by way of storing charges. It is actually by way of a different resistance level. So the top wire, metal wire on top and the metal wire on the bottom, when you enable them, you would select one particular cell. And by passing different currents to this wire, you would change the resistance of the particular cell. So therefore, even if you power down the server, right, the resistance remain the same. Therefore, the 0-1 states are being retained in the particular persistent memory media. So in summary, the persistent memory has a different storage physics. Basically, it is not a transistor, it is a threshold switch. And a bit is accessed by a current sent through the top and bottom wire, touching each cell. And cells can be stacked in 3-dimensional for higher capacities. And by storing different resistance states, it retains a 0 or 1 status. And therefore, they can retain their value indefinitely even when there is a power loss. Now, to distinguish write operation versus read, a different voltage is applied across the cell. So it would effectively program the cell to a different resistance. Now, as you can see in this pyramid, this is illustrating the economic of scale for using PRAM. So PMEM sits nicely in between the DRAM and the SSD. So therefore, it provides a high performance, high endurance, but with a lower cost than the DRAM. So in using Aerospike, we can configure it in different modes. The original mode that we have been using it was having the index in DRAM and the data in SSD, as I mentioned a few times. The other extreme is to even store the data in the DRAM, and needless to say, it would be very expensive. So you can, with the PMEM, you can store the data in the PMEM also. But since PMEM is also more expensive than SSD, a further compromise would be, or trade-off, would be the middle column, whereby we would store the index on the PMEM, but the data in SSD. And the DRAM will simply use as an internal high-speed cache, which is not storing the index anymore. So in summary, when we compare the three kind of configuration, as you can see, for speed, DRAM is the fastest. Persistent memory is a little bit slower, but it is much faster than the flash memory. And the cause is that DRAM is very expensive, as you know, and the persistent memory is a little bit less, but more than the SSD. But the main point in this presentation is the fact that persistent memory is non-volatile. And in our second half of the presentation, we are going to show you how this particular fact that it's non-volatile benefit PayPal from an operational perspective. And the latency is that PMEM is almost as fast as the DRAM. So that's the main advantage. In terms of reliability, right? The PMEM has excellent read response time compared with flash-based drive. And then endurance is one also very important factor. In terms of the wear and tear, the PMEM is actually quite high in endurance. So finally, this is a diagram illustrating how we use the PMEM. So we have 4 SSD, each one of them is 6.4 terabyte for a total of 24 terabyte per server. So we have a huge storage on a per server basis. And imagine today we have 2,000 hosts, right? You multiply that, that is an enormous amount of capacity. Now the PMEM fits nicely into our DIMM slot. So in our hardware configuration, we purchase additional PMEM in addition to the DRAM, and we just put them into the DIMM slots. Now, I don't want to go into the detail of the configuration since it's not really relevant to the main theme of the presentation. So in summary, at the end of 2021, by using this hardware configuration, we were able to reduce our footprint from supposedly 2,600 servers down to 1,300 servers. And from a number of racks point of view, we reduce it from 60 to 44. Obviously, some of the racks are not fully filled. Otherwise, it should be exactly half of 60. And as I mentioned earlier, this would comprise about 150 clusters. And today we have more than 10 application teams using this platform. And the number of hosts that are connected to this platform are more than 10,000. And as an ecosystem, we are supporting more than 500 developers within PayPal. So in the next session, my colleague Deepti, she's going to present to you the statistic of the improvement we gain from using the persistent memory. So Deepti, you can switch to your screen. I'm going to hand off to my colleague. I'm going to start my sharing.
Yeah, thanks, Vincent.
Yeah. Yeah, while we're waiting, I'd like to reserve any question and answer to the end of the session, if there is any. Meantime, also, John can help us to answer some of the questions, if there is any.
So, Vincent, just to check, is my screen visible?
Yeah, I'm seeing your background.
Okay. Do you see the slides now?
Yes, you can put it in presentation mode.
Oh, was it?
Are you bringing up your PowerPoint?
Deepti, I would suggest that you disconnect the additional monitor and you put yourself in presentation mode. So we will tell you if we can see you.
While we are waiting for Deepti, if there is any questions, attendees, feel free to raise your hand so that Vincent can answer your questions.
That's right. Great.
Hey, my question is like, is there any limit like how much PMEM we can like set up on a host?
I don't think so. It's limited by your number of Steam slot in your hardware, right?
But DIMM
So
slot is like the replacement of DRAM. How about like with SSDs? Like if you want to replace with SSDs, then does it go in like DMEM slot or like it is go to like your SSD slot?
there is different form factor. So the one I show you is only for replacement for DIMM. And yeah, I believe there are different form factor that you can use them to replace SSD.
Yeah, because like
So
if you want to store whole database into PMEM, like the in your case, in
yeah,
that case, we have to replace SSDs with PMEM. In that case, like I'm just wondering like how much is the maximum capacity like we can go, and what is the process to get it in the server?
yeah, I think different vendor when they build a server, right? They have different configuration. So I would say the limit would be depending on the vendor, but obviously it should be doable because that's why they come up with this technology to be able to replace SSD if you decide the performance. Yeah. So the limit would be like, specific to a specific vendor. I don't have the number with me off my head.
Okay, thank you.
Yeah. All right, great. Hey, Deepti, I'm seeing a slide. Yeah.
Okay, thank you, Vincent.
Uh,
I can get started. And sorry for the glitch there.
yeah, Deepti, I stopped your video. You can start your video. Yeah.
Okay, thank you. Yeah. So thank you, Vincent, for the insight on the persistent memory. So good morning, everyone. And as you've seen that in the first half of the presentation, we have covered about the persistent memory architecture and also the Aerospike database configuration, how it looks like in PayPal. So in this part of presentation, I'll mainly touch upon the persistent memory, like how it's playing a major role in improvising the database indexing in Aerospike. And for that, I'll be just going over some of the concepts of storage architectures, and then we'll try to understand what is indexing, why it is important, and what is the difference when we index with DRAM or persistent memory. And we'll follow with some of the stats where we'll show the comparison between persistent memory and DRAM, and finally concluding with the overall gains or benefits that we are achieving using persistent memory. So we'll get started with the storage architecture. So as we know that Aerospike is a key value distributed database where all the data is stored in key value form. And there are three main ways of storing the data in Aerospike. The first is in memory, the second is all flash, and the third is hybrid. So in-memory database, it gives us super fast speed, but then we do have a couple of disadvantages associated with the in-memory architecture. The first one is, of course, the high cost, and the second one will be the long reboot times. So in case of server failures or whenever we have to do any maintenance activity which requires OS reboot, so it takes very long time for the servers to reboot. And for a financial company like PayPal, that may not be acceptable because then it results into maybe poor customer experience or loss of revenue as well. So in the second option, if we consider the all flash, then it too reduces our cost, but then it has high latency. And again, in the real world payment system, that does not suit us. So in PayPal, we have opted for the hybrid architecture, in which we are storing the indexes in memory and the data is in disk. So the benefits that come with hybrid memory is that it gives us low latency, like it's somewhere in between in memory and all flash, and also the cost is in between. So it's reducing our cost, but at the same time, it's also reducing the time to recover for the databases. But still, with hybrid memory, we have a challenge. It's the same, the long reboot times. So we'll look in the coming slides how we are overcoming that challenge of reboot times there. But before we understand like how we are tackling that challenge, we'll understand a little more about the process of indexing in Aerospike to get a better understanding of how persistent memory is enabling us in indexing faster. So in Aerospike, the index architecture, like index, can be divided into 5 main components. The first will be the digest hash key value, which basically represents where the data, I would say, where the data is stored, like which node of the cluster the data is stored. And the second is the write generation count, that means how many times a record has been written. The third is the expiration time, that is time to live. Fourth is the last update time, and the fifth will be the storage address. Now, like if you notice here, the contents of the index are very much derived from the data itself. So we can rebuild the indexes anytime if we have to. So especially in case of OS patching, like whenever the servers are rebooted, so at that time we are rebuilding those indexes. So we'll make use of the same concept when we explain in further slides that how we are re-indexing and how we are reducing the time for the indexes. Now, along with it, we also know that storage space required for any index is 64 bytes. And knowing that, like if we know how many keys or what amount of data we want to store in the database, like how many keys we are planning to store, it's easy to get an estimate of how much memory we will require. Say in case we have to do the capacity estimation, like how much PMEM is required or how much DRAM is required. So this estimation can help us there. So now let's understand the process of indexing here. So the primary indexes in Aerospike are stored in the Linux shared memory. And what happens during OS reboots that because the indexes are stored in the shared memory that is volatile in nature, so whenever the server goes down, the indexes are lost from there. And then we have to rebuild the indexes from the data in the disk. And this is the same point that we were emphasizing on in our previous slide, that indexes can be rebuilt from the data in the disk. And the same index rebuilding thing is being used during OS reboots, which is taking time here. So if we see the average re-indexing time for a typical 2 billion keys is 40 minutes. And so in distributed system, apart from re-indexing, there is another activity that gets kicked in whenever a node is taken out, and that is a rebalancing activity. So we'll see that in the coming slides, and that also takes around 3 to 4 hours. So if we have to calculate the total time, it will be somewhere around 4 to 5 hours that total time will be taking for re-indexing and rebalancing. But now when we introduce persistent memory in place of DRAM, the indexing time reduces to 10 seconds. And that is negligible as compared to 40 minutes. So on the left-hand side of this slide, you can see the stats that how much time is being taken for re-indexing in case we are using shared memory or we are using persistent memory. So for 2 billion keys in shared memory, it's taking 40 minutes, whereas the same number of keys in persistent memory in taking 10 seconds. And even if we increase the number of keys to 13 billion, it's still less than a minute. So that is a big improvement for our environment. And now let's take an example of maintenance activity wherein we are patching a node. So in this diagram, in this slide, you can see that it's divided into two parts. One is showing, the left-hand side is showing re-indexing, where we are making use of DRAM. And on the right-hand side, you can see that there's a graph which is showing the re-indexing timing using persistent memory. So in the left-hand side, if we see, the re-indexing here is taking around 40 minutes. And the rebalancing time is taking around 3 years, which we discussed in the previous slides. So this rebalancing, let me just give a brief on what rebalancing is. So in a distributed system, whenever a node goes out, so data in that node has to be distributed across all other nodes that exist in the cluster. So basically, the data has to be replicated, and that process is called rebalancing. And that process is taking here 3 hours, and the reindexing is taking 40 minutes. So this is for one node. So each spike in this graph, it represents one node each. So basically, it's sorry about that. Yeah, we are showing here that OS patching cycles of all the nodes in a cluster in a rolling fashion. And on the right-hand side, we are showing that it's taking the reindexing time is 10 seconds. Now, the question that we are getting at right now is that how is that reindexing time decreasing to 10 seconds? So if we look if we pay attention here, that why the reindexing time has reduced to 10 seconds, it's basically because we are making use of persistent memory. And as Vincent covered earlier, the persistent memory is helping us persist the indexes in the memory. And how is that happening? If we, let me go to my previous slide to explain it better. So here we are saying that the primary indexes are getting stored in shared memory. But in case of persistent memory, those indexes will be stored in persistent memory. So whenever we are rebooting our servers, so whenever any server is getting restarted, the indexes persist in the persistent memory. They are not getting lost. So what happens as the server process comes up, it reattaches itself to the persistent memory, which has the indexes in it. And that state, because the indexes are not lost and we do not have to rebuild those indexes from the data, the time gets saved there. So after the server process attaches itself to the persistent memory, it rebuilds some internal state and joins the cluster within few seconds. So our time gets saved there because the data is not being scanned on the disk to rebuild the indexes here. And that is what we are making use of here. Whenever we are patching, the reindexing time is reducing from 40 to 10 minutes. So that was the time that we shared for one node. Now, if we have to look at our whole inventory, so our inventory has around 56 cluster groups, and each cluster group is comprising of 3 clusters, one for primary, LDR, and the DR. And on an average, each cluster has 10 nodes. So we have around 1,700 servers in total. So if one server gets patched in, say, 1 to 2 hours, and with PMEM, we are reducing the time to 30 to 45 minutes, and that is around half the time. And same is the case with one cluster where we have reduced the timing from 10 to 12 hours to 5 to 6 hours. And now if we talk about our whole inventory, we are saving more than a month time. So that is a 2x improvement in terms of OS patching cycle. So earlier our patching cycle used to be 90 days. But now it's getting more, the patching SLA is getting more stringent, and we have to now patch the entire inventory within 30 days. And with the introduction of PMEM, we are quite confident that we'll be able to achieve our targets of 30 days as well. And in this slide, I'm sharing some of the stats apart from indexing. So the benefits that we are achieving using the persistent memory, because re-indexing, so far we have only focused on re-indexing, But that is not the only advantage we have achieved using the persistent memory. So another main, I would say, the main benefit that we are getting is the high density. So here, if we, with persistent memory, we are able to now have more denser hardware, denser nodes, wherein we can store more data. So earlier, one node used to store around 3.2 terabytes of data, which can now store 12.8 terabytes of data. So here, HT means high density, that is persistent memory, and ST means standard density. So we can see that the density of the storage density on the nodes has increased by 4x times. And with this increase in the density, also we are storing now more number of keys per node. So earlier the number of nodes used to be 2 billion, which has now increased to 10 billion, which is 5x improvement. And with this improvement, now we require lesser number of nodes per cluster for the storage. So the number of nodes have reduced from 20 to 10. So that is again a 2x improvement. And with this, we are getting more savings in terms of rack, power, and space in data centers. And overall, our cluster group cost has dropped by 30%. So also now with the higher density, we have increased our replication factor. We are able to increase the replication factor from 2 to 3. And that means now we have more fault tolerance. So earlier, if 2 nodes were going out of the cluster, so there were chances that we will lose some data. But now, as the replication factor has been moved to 3, like even if 2 nodes are going out, we are confident that we'll survive without losing any data. And so correspondingly, the clusters racks, there is an improvement there. And we have already covered about the re-indexing and reboot times, like how much savings we are making in the re-indexing and reboot times over there. So now, what was the, like, how did we start actually the implementation of the PMEM? So we did our first POC in 2019 on PMEM. And then in 2020, we got an opportunity to upgrade our environment with a project. So where we were migrating all our clusters from one data center to another. So that we called as DCX. So there we upgraded majority of our clusters, and now only a few of our clusters are on older SKU and are 20 node clusters. But also another additional influencer for the upgrade of the environment was the OS patching. So OS vulnerabilities are kind of number one priorities for PayPal right now, because it's a financial company, and we have to patch the servers as soon as any new kernel version is available. So we have an SLA of 30 days there that we have to patch it. So with PMEM, we are able to patch all the servers within our SLA. So that was a major influencer. And with PMEM, we are able to do so because the re-indexing time has increased, and also the storage density for our clusters have increased. So now we have lesser number of nodes that we have to patch. So it's kind of lower operational cost for us now. So we can just say that as part of like as an outcome, like for using the persistent memory, the improvement is multifold here, because we are able to patch our clusters within an SLA of 30 days. So that is one, because of lesser number of servers. And then we also have storage optimization, because lesser nodes are storing the same amount of data for us. And the third is that because persistent memory has almost similar throughput as DRAM, and it has very low latency, it is giving us better performance. And also the operational cost has gone down. So in this slide, this is just a depiction of our data center migration journey, where we are showing like how many clusters have been migrated or how many new servers have been built. But the three main key points that we want to take away from this particular diagram is that first is the quarterly DB or OS patching cycle, which has improved 3x time. So we have improved it, like earlier it was quarterly, now it is monthly. And the second one is the lesser inventory, because with the higher density, earlier our server inventory was 2,600 servers, which has now reduced to 1,300 servers. So we have less of inventory to manage. And the third is the higher density. So earlier, we used to store 6 terabytes of data per node. And now we are able to store 24 terabytes of data per node. So that has given us more denser hardware. So here, we will just like to conclude with 2 statements here, that performance and cost are not the only important consideration for using PMEM. Operational consideration has far-reaching consequence in data recovery time and operational efficiencies. Yeah, thank you. Now, we are open for any questions.
Yeah, thank you, Deepti, for the nice presentation, and Vincent Chong for throwing up a lot of insights into persistence memory. There is a question on the Q&A, like, do you see more corruption issue with PMEM as compared to SSD, or any other no disadvantage of PMEM? So basic thing is, like, everyone wants to know, when you talk about good things, what we should not do, because we don't want to burn our fingers with the same thing that has been already done. We don't want to reinvent the wheel. So what is some insights, or what bad experience you had, which you will like to pass on to other customers to avoid?
Yeah,
Okay,
yeah, I
so-
can take that question. Deepti, you want to take it? Go ahead.
No, Vincent, please go ahead.
Yeah, I was just going to say, we have been using PMEM for about a year now. So far, to be honest with you, we have not seen much of a negative in terms of performance. But we noticed that from time to time, the PMEM partition somehow will be dropped. And we have to, when that happens, right, we have to remount the partition and restart the node. So that's the only thing we have been seeing happening from time to time. But that is within our degree of tolerance, because we have a replication factor of 3 due to the fact that we have higher capacity, right? So all in all, I would say so far we haven't seen any big negative other than what I just mentioned. Yeah, so we are quite optimistic in terms of continuing using this technology going forward. Deepti,
Yeah,
you want to add anything? Yeah, okay.
Go ahead, Deepti.
Yeah, I was just saying that the only thing that we need to take care here, maybe that the configuration that PMEM requires. So if that goes missing, then we will see a deterioration in, I would say, indexing. So there are few configurations at the system level that we need to take care. But other than that, like with PMEM, we have seen mainly all benefits only, like nothing major that we can say, okay, these are the, I would say, some things to take care of.
Yeah, I just want to also add, one reason why we increased the replication factor from 2 to 3 is because, like you, we were not sure.
I believe, Vincent, we lost your audio. Philip,
About the stability of the losing the partition. So yeah, so we have a higher replication factor to handle that. But going forward, if we observe improvement on that, we might even drop the replication factor back to 2.
thank you. Philip, you can go ahead and talk. I have unmuted you.
Okay, so I understand why creating an index is so much faster with PMEM. You don't have to rebuild it from scratch. But why is rebalancing an index so much faster? Don't you still have to do about the same work in both types of memory?
Yeah, in terms of rebalancing, it's not faster. It is marginally different, but yeah, you are right, because data has to be moved between nodes. When, let's say, a node left the cluster, the rest of the node has to replicate the missing copy, right, from whatever the number of Kang is. And then when the node came back, the rest of the node has to give back the copy to that node when it come back. So that activities remain the same. Yeah.
Okay, yeah, I thought the slides suggested that rebuilding was faster, so you're saying it's not.
Yeah.
The rebalancing, rather.
Yeah, the rebalancing itself is not, because it concerns with moving data between nodes. It has nothing much to do with the index itself.
Okay, thank you.
Philip, thanks for asking the question. And we have our own Oracle product managers and experts out there. Ashish, you want to talk it out so that everyone hears you rather than going through the chat? Or Doug, do you want to talk about the Exadata thingy?
Christian Shea can talk about Exadata. I can talk about times 10.
Yeah, go ahead, Doug. Yeah.
Just, I mean, Intel persistent memory is a great technology. I agree with everything that's been said. You know, it's fast, it's cheap, it works with products like times 10 out of the box, and it certainly helps with Exadata. I'm sure Christian can add to that.
Hey, this is Ashish. Yeah, so for Exadata, we use Intel Optane PMEM natively in the storage server layer. And we have to put in special code so that we have to make sure that all database, that is Oracle database intrinsic operations such as recovery or the Exadata operations such as smart scan and everything, none of those all work transparently. And so what we have observed is compared to previous generations of Exadata, the way we are using PMEM, that has enabled us to get 10x, at least 10x improvement in IO latency. Our end-to-end database SQL IO latency has improved. I think the number is around 19 microseconds with X8M. And those are the benefits that PMEM provides, especially in the OLTP layer. So that would be quite interesting. So the way we use PMEM is slightly different from the way that was described in the previous session. We use in the shared storage layer, so all database processing can take advantage of it transparently.
You know, I was going to say, in addition to how we use PMM and Exadata, we also have, somebody just mentioned here, 19.12. We just released 19.12 for non-Exadata systems, supports persistent memory database. So that's you know, Oracle database on persistent memory directly. So it's a different architecture. It's in this, it's storage or server side persistent memory, whereas Exadata is the storage side persistent memory.
And Chris, in this context, maybe in Zoom chat, you may want to mention the Moss note that you authored, so that would be relevant to all the audience here.
Right. So we have some. So 19.12 is the first support that we've got for persistent memory, and I can send the Moss notes on that.